Unlucky dude. Lucky and unlucky dude. Uh-oh. There we go.
You should convince him to go back and go on his trip this weekend so we don't have to go to class on Friday.
I agree.
What's he doing now? He's
He
not.
was supposed to be going on a trip, but
Yeah.
his buddy canceled. So now he's not going on the trip, so now we're going to have class.
I was told I wasn't allowed to tell you about this trip. Because he said, he said that he was going to let you know on Thursday, and it was going to be a surprise. But then, so I was sworn to secrecy. Yeah. Well,
You
good.
swore me to secrecy. I still told you.
Yeah, I know.
That came back
That's
on
what I
me,
told
so-
him. That's what I told Kyle. I was like, well, I kind of owe them because they're tattling on you, so I owe them. I'm going to, and so.
How'd Tim find out?
Two-way street, yeah.
How'd Tim find out it was me?
He didn't. You gave it away. He just assumed it, and you didn't deny it. It was a classic trick,
got me.
right?
He got me.
He got you, right? It was just like he was just like, oh, I think it's Kyle. And I didn't say. I didn't deny. I did. The only thing that I broke on was I was using pronouns. I said he, and so I said, oh, it's a he. And then he just threw out your name, and then he confronted you, and you gave it away.
He doesn't really narrow it down that much in engineering.
Yeah, you're right. I took out just a
Of the
couple.
overlap
Just a
between
couple.
the two classes.
Yeah.
If you said she, that would have
Yeah, it gets close.
It would be.
We'll just wait till this group in the back is ready to go here. We do have to wait for this to stop.
I think we might as well just call it a day.
Thomas, would you hit that light switch there? Just on this side.
I think we should
Yeah.
We should get like an air horn or something. As soon as they stop making noise, just
Do it back to them.
yeah.
Are they taking out windows now, Mike? Or
What's that?
Are they taking out windows now? Or?
I don't know what they're doing. The windows are gone,
The windows are
or
gone.
the eyebrows are gone. So they have to paint them afterwards and stuff. They have to like put some like epoxy on them or something.
Yeah, because I think they said they were throwing some flashing up around it too.
Yeah.
So this should be done by like.
They said December.
All right, let's do this. Are you guys ready? You got Kira, you ready to go here? I just don't want to interrupt you. Just let me know when you're ready. So all right, so let's do. Let's just keep going with this. So these are Magnell diagrams, but we talked about these are the ways that we design it. We talked about we're kind of done with the elastic analysis. You're working on a homework associated with this, or you should be working on a homework associated with this. We talked about debonding the pre-stressing because near the ends, if you have a constant eccentricity, you have this internal moment, and then there's no external moment to cancel it out, and so then you could end up with cracking up at the top. But if we debond it near the end, it'll make it, or you harp it, right? Or you drape it or something like that to prevent it from having some problems there. Okay, and so what we were in the middle of talking about now was this statically indeterminate beams. Okay, when you have statically indeterminate beams, some weird things can happen, right? And so if we have just the pre-stressing only, right? So we're gonna break this thing into pre-stressing and then what the effects it has. So pre-stressing, you basically get the effect would be, our moments would look like this. They're not exactly like this. Oh, I'm gonna make it they're not exactly like this because there is the whole development length thing that's happening, and it takes a while to ramp up. It's more of it actually, in reality, because of development lengths, it's more like this. Right? It kind of ramps up on either end. But just theoretically, if we ignore that component, you get a constant internal moment from this, right? Because you have that pre-stressing is causing this thing to pop up, which is like two big forces down at the bottom, and it's constant along the entire length, right? Also, I said this last time, you wouldn't do this, right? You wouldn't have that pre-stressing along the bottom knowing that it's supported in the middle. But this is just for just describing what's happening, okay? So we have that pre-stress only. This will cause the thing to want to pop up, right? You're causing this negative moment, right? It's going to make this thing pop up. Or you could think of these things as, this is what the moments would look like, right? Right? Kind of going like this, and it's going to make it want to pop up like that, right? But then it can't pop up like that because there is this component right here. There's this point right here, right? Even though we always draw it as like a bearing, just like a roller. Really, it does provide a vertical load is there as well, right? And so then that would cause a moment or a force that looks like this, right? The reaction would cause a downward force in the middle, right? And the moments from that would look like, oop, I don't want that. I want solid lines. That work? Boop. Right? Your moments from there would look like that. And this would be, PL over 4, right? Right? And kind of what that moment would look like from just a point load in the middle. Okay? And then the total loads, or the total moment, would be the combination of both of those things. Right? Maybe something like this. Oh, maybe something like this. Beep. Right. The total would look like that, right? These moments, right? These moments caused by that fixed support, Stanton calls them the secondary moments. Call them secondary moments because they're not from an external load. They're actually from the internal load, and they come about because of that support condition there, and they resist the motion, the deflections that internal moment would want to cause. And Kyle, when he teaches our class on these come about a lot, like I mentioned before, in post-tension floor design, because you're going like this as you go along, and you're not going to be perfect with that as you're going up and down as you go across. And there's going to be parts where you have this secondary moment that comes about, okay? And they call this hyperstatic. They're called hyperstatic moments. That's how you use it. I had never heard that term. Stanton doesn't use that term, but Kyle uses that term. Everybody kind of see that? This is a thing, and we're going to see it at some point. That's about all I want you to do with it. We're not actually going to calculate any of the stuff, but just that this exists, and be wary of it. And then computer programs will calculate it for you because it gets pretty complicated. So that's it. That's elastic analysis, right? So all this is enough for you to get through your homework on time, due Friday. You can do it, okay? I will say if you haven't got your homework 1 in yet, I'm going to start grading those today and tomorrow. So get them in by then. Okay? I know.
Whoa!
I already called Hudson out, but you got yours in. No, did you get yours in? I didn't see yours in there.
Yeah.
You did? I did.
Grade school?
Yeah.
Yeah.
I didn't see it. You look. Good acting, by the way. It's okay. Any other guilty people? By the way, I heard Will 1 just got demoted back down to Will 3. But Tim's not willing to put you up at Will 2 yet.
What?
Because he's not going to grad school. So he bumped it back down. He said he's not going to grad school. So Tim demoted him back down to Will 3. So currently there's no Will 1.
Still will too.
You're still Will 2. Yeah, he didn't promote you. You're still Will 2. Just to make sure you call Will out when you see him, that he's back down to Will 3. And then he was arguing this morning that he wasn't technically Will, that he wasn't Will 3 again, and he was having a conversation. And then Tim walked around the corner and goes, "Oh yeah, you're Will 3." So it's happening. Cracking. Okay, so things that we dealt with in service loads, just kind of point these things out. What we cared about is cracking. We cared about compression limits, compression and tension limits. And this is backwards, right? Usually, and then we define deflections. Usually we care about, life safety first, but in pre-stress, we flip it around, right? This is all elastic analysis. This is just throwing some words out there, right? We deal with service loads when we do these things, okay? And then people don't die. If you mess this up. People don't die if you mess this up, right? And because of that, use service loads. You're doing elastic analysis, but we do start with service. Okay, we haven't talked about deflections yet. That's coming. That's one of the next things we're going to look at is calculating deflection. It turns out it's really hard, but we have looked at the cracking and the compression and tension limits, and that's it. We have done that so far. Okay, but now we obviously we do care if people die. So after you get done with designing the beam to meet the requirements up above, we then come back and we design for the ultimate load. Right? People could die if you mess this up. Right? Therefore, we use load factors and fee factors. Right? Thus far, we haven't used those. Right? There hasn't been any talk of factoring our loads or reducing our capacities. Right? That's what they do. Right? With the LRFD, we pretend our loads are bigger than they actually are. And then we pretend our capacities are less than they actually are. And then that way we have factors of safety coming from both sides. Okay? And so we also use nonlinear analysis. This. What up, new? More accurate. Less conservative. Right? And what we're going to talk about in this class, bless you, these are what we have to make sure happens. Phi mn has to be greater than or equal to mu, and phi vn has to be greater than or equal to vu. We're going to do both of these. We're going to start out with the moment capacity. Right? Not so much on them, and we're not going to spend much time on MU, what our demands are, but we are going to focus on the phi mn side of things, right? And then we'll go on to phi vn, which actually gets pretty complicated when we do that. Also, you'd be surprised how many people mess this up in structures too. They flip these around. They say that phi mn has to be less than mu, and it's you've probably seen it in some homeworks, right, Kira? No, you haven't seen it yet. On exams, people throw that. They flip that around, and they're like, that worked. Therefore, you're okay. You're like, oh my god. Oh my god. We're gonna guarantee people are gonna die. It's just like, yeah, that seems pretty obvious, but then capacity has to be greater than demand, right? And if you flip that, then it's. I think it's just a brain fart, but it's still like they're panicking on an exam, but it's still pretty funny.
Do they just mix up the variables, or do they mix up the numbers too?
I know they calculate this number and they calculate that number, and they're like, great, and then it'll be not good, and they'll say, oh, that because that worked, we're good to go. You're like, oh god, the opposite, for fuck's sake. If you get anything out of this class, make sure your capacity exceeds the demand, no matter what. And then they mess it up. At least you see, you find the point where they bifurcate. But now, what's like I write there, I just want to pull the card, be like, all right, you're done. You're not going. Just it's done. You're out. You're out. Okay. So when we calculate this, and I got to mention this. This is the first. This hurts me. Is as an academic, I really like this thing called strain compatibility way of calculating capacities, and it takes literally 3 days to teach you guys how to do it. And this year, I'm not gonna fucking do it, and it pisses me off. All our notes have it built into it, so I got to work my way around. And what I want to show you, I'm as an academic, I'm gonna still discuss it with you a little bit, but I'm not gonna make you do it. And the reason for that is I want to spend more time on post-tension floor design, because I know as a real engineer, you will never use strain compatibility, even though it's super cool. You won't do it. You won't do it in the real world, and it pains me to do this. And we'll see. When we get to it, I might just be like, fuck it. We're gonna do it. I'm gonna teach you it anyway. Okay,
You could record it and then post the videos as optional.
As an optional learning.
Over under 3 views.
There's some nerds in here that would dive in a little bit.
3?
Three would do it.
If you watch it, it's extra credit.
Yeah, or maybe something like that, yeah. Or if you do it on your homework, you can do it extra credit. Stanton talks about it in his stuff. And actually, you have to program a little bit, and like with ChatGPT, I bet you could get it to do it for you. But regardless, I don't want to spend too much time doing it. So just basically, this is just a review of, and we'll talk about how it differs from pre-stressed concrete. But this is just a review of just standard. You would do this on a regular reinforced concrete as well, right? So you start out. Here's what your cross section looks like, and you got your big pre-stressing down at the bottom, right? And so this is obviously a T-shaped section. So what you do is you start out with the strains, right? You make the same assumptions of, plane sections remain plane. You have a strain distribution going across like this. What is this strain up here at the top? Oh, you sons of bitches. What's that strain at the top? Yeah, 0.003. Right? We make that assumption always that's the strain at which concrete crushes. We still make that assumption. The strain in the concrete is going to be 0.003, right? Down at the bottom right here, we'll call this epsilon sub PS or epsilon sub PU. It'll be one of those. We'll differentiate them in a little bit, okay? Given those strains, given the strain distribution like that, and assume that it's linear, okay, given those strains, right, you can calculate where that neutral axis is. That's going to be a function of x. That distance right there is going to be x. That's what we end up ultimately solving for, is where that neutral axis is, right? So it's kind of unknown when we go in here is what that neutral axis is, right? What my actual concrete strains are doing is this, or stresses rather. It's a nonlinear stress distribution, right? This right here would be your F prime C. Down here at the bottom, you'd have FPS. Our stress in our pre-stressing would be what we call FPS down at the bottom, right? To make things a little bit easier, we use this block right here. What's that block called? Whitney stress block. So this is all just review on regular reinforced concrete. We use the same mechanics, right? 0.85 F prime C is that dimension. This dimension is beta 1 times X, right? We call A a lot of times. Okay. Same thing down here. This is still just FPS. Okay, and so that's what you do. You go strain, you go section, strain, stresses, equivalent stresses, and then you go on to forces, right? You take the forces, you just take these stresses down here, right, and multiply them by their areas. So up here, this is just going to be C is equal to 0.85 F prime C, A times B. Right. This would be B up here. This would only work if it stays up. That only works if it stays up in the web up there. This equation right here only works if it stays up there. If it starts dipping down, then you have to do more stuff to it. There'll be more components that go in that compression force, right? And then down at the bottom, that T, FPS times AP. That's an F there. Times AP, okay? And what we do to solve this, right? Like I said, the only unknown in this, well, there's a couple unknowns, we'll talk about that. But really, usually, if I know what my FPS is, if I could tell you what the FPS is, the only unknown in this is that A, that where the neutral axis is. So what you do is that this T has to be equal to this C, right? C equals T, that has to happen, otherwise this thing would be accelerating, right? It would be spinning, right? Right? So C has to be equal to T to have that equilibrium, right? And so that's what you do. You set C equal to T, you apply equilibrium, apply equilibrium, and solve for A or X. Right? What that is, A or X. By applying that, right, you set C equal to T. But where things get complicated, you're like, oh, I could do that. Where things get complicated is, what do you use for FPS? Right? In regular reinforced concrete, right, we assume that that's FY, right? We assume, and actually the code tells you that that has to happen, right? If you're doing a regular reinforced concrete beam, your steel has to yield, right? You have to go beyond that yield. We don't have a yield point because this is the pre-stressing strands, right? These are the pre-stressing. They don't have a yield point, right? And then to complicate it even further, right? This is what, just got to show you, right? This is where, there's my axes. You got FPS on that axis, and then we have epsilon sub PS on this axis, and it goes like this, right? It has like a kind of a linear region, and then she goes kind of like that. Okay. And so what do we use? But it's not, FY doesn't necessarily make sense, right? And then also to complicate things, right when you start this, before you've even loaded this, that steel is already loaded, right? Because it's been stretched first, right? You stretch it first, you cast the concrete, and then you release it. So it has an FPS in it to begin with. That's our pre-stressing force. So it's already being squished. So you start here someplace, right? You've already stressed it out to there. And then you're applying a load, and then now that load is going to change. You know, and when elastic analysis, we assume that the load didn't change FPS. Now it does, right? Now we're talking about ultimate loads right at failure. Now there's a bunch of deflection that happens, and it's going to move to failure out here someplace, right? It doesn't have to be at the peak, but it's just going to move to the right some at failure. Right. Tendons start this process already stressed. Stress then moves to right when ultimate loads are applied. But how far? Right. Now it's so quiet. Okay? And so right now I'm just setting the stage for this, right? Is that they're going to move to the right. They're already pre-stressed. They're going to move to the right. There is no such thing as like an FY necessarily. So what are they going to go to, right? And that's where this like strain compatibility comes in. Is like if I had this equation, right? If I had this written as an equation, I could calculate what the amount of strain it's at and then what the strain's going to at failure. And then I could just, plug it into this equation and get what FPS is. And that's strain compatibility. It's beautiful, okay? Or what you're really gonna do is the code gives you a value for that. Right? I know that's what you're gonna do. You're lazy, except for three of you. And honestly, I would do it too. Just because you can make mistakes if you're trying to do it. You gain very little by doing the strain compatibility. And so ACI has, they're like, they punt, right? They just say, hey, here's an empirical equation for what you use for FPS, period. Right? And it's a function, it's empirical, so it's a function of a bunch of properties of the cross section. We'll look at it in a few minutes. But you just go through and it calculates FPS. So then you come back to this, and then this is going to be a known value that we get from the code, and then this, the only unknown is going to be A, and we solve for A and then move on. So, but there are some other differences as well. But I'm setting the stage for what we do. Oh, it's so fun. It's so fun to put in there's a thing called Minigato Pinto. Who doesn't want to say that, right? Like when you solve this thing. Okay, so where's this defined? Like how do you calculate this? This is ACI chapter 22. It's under the same section that you do for regular reinforced concrete, right? This is chapter 2, right? Sectional strength and this is where you find it. And you may not have noticed this. This is where they define all, you have to, equilibrium and strain compatibility, and then equilibrium is satisfied at each section, right? It's interesting how they, Tim, obviously shits on concrete a lot, right? Because it's a big guessing game where steel is just like pure and there's exact answers for things, and like when you say the capacity is going to be something, it actually is that, right? If you don't remember Structures 2, when you pull those things, it's exactly right, exactly how you calculated it. I just think that the reason Tim likes steel so much is because it's easy. And his puny brain can't handle the complexities of concrete. And if you're a true concrete man, you're smart enough to do it. But again, I guess my point is saying this. I mean, concrete, it's right, it's mixed with a shovel, right? It's a bunch of rocks, and it's weird, right? And then it is guessing, because it does break at really weird things, and he's absolutely right. And it is hard, and it is confusing, and the code is weird, how it's structured, and there's stuff in one spot, and then way over in another spot. It's like all over the place, and you just got to be really... You gotta be part of the brotherhood. You gotta know, like you just know, right? Like what each of these things are and where to find things. But if you actually look at it, right, and look to see where it calculates this stuff, it never really says like use this equation for calculating capacity. In the code, in words, it tells you this. Right? But it doesn't ever lay it out. It never shows you a picture for doing it. It just says, oh, look, your stresses can either be this, or you could use the Whitney stress block like this. You have to make sure equilibrium applies, but then you have to make sure that these strains down below reach a certain value and stuff. It's really spread out all over the place. But I just wanted to show you where it does mention pre-stressing. So this is chapter 22. We work our way through chapter 22. All the same stuff. Here's your 0.003 for the extreme compression fiber that we talked about. Tensile strength shall be neglected, right? We ignore, I guess I left that part out, right? Right? When this goes into tension, right? When this goes into tension, we just ignore the concrete. Technically, though, the concrete does have some tensile capacity. It would keep going that direction with some tensile, but we ignore it. The reason we ignore it is because it says right in here, right? Ignore it, right? It says you can ignore it. You don't have to, but you can, which most people would do that, right? Keeps going. This is where your A is beta 1 times C. It tells you what beta 1 is going to be. Here's where beta 1 is at, right? Deformed reinforcement, all this stuff down here. Development lengths, flexural strength, general. Keep going. Concrete. Oh shit. I was like, nothing's highlighted because I haven't highlighted it yet. So 22.2.1.3. 22.2.1.3 here. Oh yeah, there we go. Right? So they slip in a little, right? This is under where all of our other stuff is at. It slips this in. Strain in pre-stressed concrete and in bonded and unbonded pre-stress reinforcement shall include the strain due to effective pre-stress. Oh, no shit, right? Like, but it tells you that. That's just saying, look, you have to take into consideration that it's already been strained and stressed. Clearly, it'd be weird to not include the fact that it's already stretched, right? But it just tells you have to do it. Changes in strain for bonded pre-stress reinforcement shall be assumed to be proportional to the distance from the neutral axis. So that's just saying right, that I could calculate the strain, my additional strain in my pre-stressing based off of this point right here. Right? That I could use, the similar triangles, the 0.003, the distance x right there, and then I could calculate what this strain is and assume that that's the same strain in the pre-stressing. The additional strain in the pre-stressing, that guy, right? To the right there. And I get that from this guy right here, right? Note that it says for bonded, right? You can't make that same assumption for a post-tension, because post-tension is not bonded. The concrete and the steel can change independently of each other, right? Because they're not attached to each other. In regular reinforced concrete, you have deformed bars and concrete cast around it, and if the concrete moves, the steel moves with it. Same thing with bonded reinforcement. If the concrete moves, the steel moves with it. If it's unbonded, that's not the case. The concrete can move and the steel can stay put and it can slide around. So you have to treat the bonded or the unbonded post-tensioning different than the bonded reinforcement. Okay. That's one spot that it talks about it. 22.2.4. Yeah. Design assumption for pre-stressing. Note that how hard they're working out there. There's one person out there. The whole side of the building. They have one guy out here. He's lowering it down.
Just gonna tell him they're doing it wrong.
Get out of here.
Just tell them they did it wrong.
You did it wrong. They're gonna be out here longer. Or you can see they cut little lines for the flashing on above each window. See that? So we gotta listen to them. Oh, this is gonna be a long time. If they have to put flashing on every one. Oh, motherfucker.
They said they're gonna go till the end of October.
So excited.
And
Start back up in April.
Maybe I can. Yeah, right.
They're gonna start back up.
Maybe find us another room. Maybe find us a cool room. A cool room somewhere.
That's another room open? Is there gonna be another room
I
open?
don't know. Probably not. Probably not.
This one's supposed to be MLC.
Yeah, where you're at, right? All right. So design assumptions for pre-stressing. There's some more information here, right? For members with bonded pre-stressing reinforcement conforming to 20.3.1, stresses at nominal flexure strength (FPS) shall be calculated in accordance with 20.3.2.3. That's sons of bitches, right? They don't put it here. They put it in 20.3.2.3. I got to go over there to see what FPS is, right? That's what I'm saying. It's all the stuff all over the place. For members with unbonded pre-stressing reinforcement conforming to 20.3.1, so this is for the unbonded, right? FPS, we use this. And that's what I'm saying. We're going to do that, right? That's what you're going to do in the real world. You're going to go in, you're going to use this guy, or you're going to use this guy. These are just two empirical equations. We'll look at them in a few minutes. You calculate them based off of the material properties, and then you move from there, right? That's what I would recommend doing, right? If embedded length for pre-stressing strand is less than LD, the design strand shall not exceed the value given in. So it's basically if you haven't gotten development length, you can't go beyond a certain value. Okay, we go down to flexural strength, pre-stressed concrete members, another part right here, 20.3.2.23 point. Oh. Okay, right here, 20.3.2. Yeah, right here. Okay. Deformed reinforcement conforming to 20.2.1, provided in conjunction with the pre-stressed reinforcement, shall be permitted to be considered to contribute to the tensile force. So you can put, and then same thing for the other non-pre-stressed reinforcement shall be permitted to be counted. So if there's other steel in there, you can count the other steel. That's what that's saying, right? And that happens sometimes. And we'll talk about why we do that. But instead of just having a big pre-stressing strand down at the bottom, you could put in mild reinforcement as well, right? You could put in just rebar in there as well. Post-tensioning, different. It's a little weird, right? Because in post-tensioning, that's really weird because it's cast within the concrete. You have the post, and then you come back and you pre-tension it, which means that you're taking all of that tension reinforcement and it's going into compression initially, right? Because you're squishing it and it squishes along with the concrete, but it gets used. And then, because then later on, when we talk about the full load, right, then that it will get engaged in the tension region when things start cracking when we apply the full load. Tension members, absolutely, they use them in there, right? Because in there, you take concrete, you have all this rebar, and you have a pre-stressing strand in there. You stress to the pre-stressing strand, your other concrete or your other steel is just waiting there, and you cast concrete around it, and then you release it. I guess same thing will happen there too, right? When you release it, those steel is going to go into compression, which is fine, right? But you get to count that steel for the ultimate load too. But it's different though, right? Because that steel is regular mild steel that has a yield plateau, right? That goes up and then it yields and goes from there. And I think, does it say something about shall be permitted to be considered to contribute to the tensile force of other non-pre-stressed shall be, no, it doesn't say anything about that. That could be FY, but it could be. So you could add in some additional regular reinforcement as well to increase your moment capacity. And if you do that, it doesn't really affect, we'll get into that. We'll talk about that later. There's some reasons why you would include that and not just include more tangent reinforcement. So that's where it's mentioned, right? So you may not have even noticed it. I guess there's pre-tension here too. It's mixed in with it. I kind of would like to see it have its own section, right? In pre-stressing, and then just talk about it like kind of as a separate thing, but instead they just mix it in with everything else. Okay. All right, so what do we use for this FPS, right? I used to talk about 3 methods. We're just going to do 2 methods. We'll still say 3 methods, but I'm not going to talk about the 3 methods. I'm just going to talk about 2 of the methods. And this is the method, this is what Stanton went through. He goes through and just says, you could just use FY. Because there is even though there isn't a real FY, there is a specified FY. The manufacturer of each of these things will give an FY. Right, it's going something like this. Right. Oh, wanted that rounded. Enough. Yep. So they will call out something. It's not real. Has to do with that offset that we talked about. That'll be FPS equal to FY. So he just says that. And you're going to do a homework where I'll give you an FY and you just plug in the FY value. Okay? Or that's one way of doing it. So your homework this week is going to be a T-shaped section. And then it's going to say calculate the moment capacity of a pre-stressed member where FPS is equal to FY, okay? They're an empirical equation, so this is that 20.3.2.3 that the earlier section of code pointed us to. And there's your equation. That sucker right there. Right, and it's empirical, right? So what empiricism does, what that comes from is from a bunch of test results. They did a bunch of tests on some members, and then they developed this equation. They noticed, oh, by the way, my FPS value is going to vary based off of gamma and beta and FPU and its relationship to F prime C and rho P, and so you have to go through and you have to it's not easy to use, right? Because you have to go through and calculate all of these values. Right? But once you calculate all those values, you just plug them in, and then it gives you a value for FPS, which that value will be really close to what FY is, but it's slightly different, and it accounts for all these other effects. Okay? Things to be careful of when you're using this. Right? You look at these, let me see. Table 20.3.3, so it tells you which to use for your gamma. So this is, I agree. Concrete's weird, right? Like, you should be getting used to this by now, right? Especially if you took concrete last semester. There's a lot of this, a lot of empiricism, and it is pretty frustrating because the other thing that ACI is really good at doing is not telling you everything, right? It's like it'll kind of lead you and be like, oh, this is the value that you should use, but there's still some unanswered questions. It's like, what do I use for that value, right? And so let's just look at some of these things just to give you an example, right? Gamma value, sure, you come down here and you look up gamma, based off of the FPY over FPU, so you'll be able to calculate that value. Beta 1 is the same beta 1 that gets used for the A, the relationship between A and X, which is going to be dependent on the concrete strength. So that, right, if it's less than 4,000, it's 0.85. If it's between 4,000 and something else, it ramps up, and then it's something else above something else. See, this is what I say, the brotherhood, right? You just got to know this shit, right? Right? So that was beta 1. So gamma, you look beta 1. Rho P, right? Rho P. Well, that's not even here, right? So that would be one of those ones where you have to go look it up at the beginning of this chapter, right? They have all the variables listed and tell you what it is. And what that is the right? Oh, I'd have to look that one up. But maybe next time. You need to. I know that in the past homework, that question has come up a lot, and I can't remember the details of what's happening. But it has to do with what you do. I remember what it was. It has to do with the fact that I give you a T section. Oh yeah, I can remember this. What is
Oh no. Isn't that the rate?
AS over BD?
Yeah.
AS over BD, right? That's what your typical row is. See, brotherhood. Thomas is part of it. He remembers. I will say, I'm not joking. In the past, I got in trouble for saying brotherhood. A student took issues with this and actually reported to the department head. I just mean that in a general term. Kira, Ahika, you guys are welcome as well. Everyone is welcome. I don't care. Everyone is welcome into the brotherhood. I started, and it was just like, oh, what's this? What's this? You know, that you're saying about the brotherhood. I'm just saying that you're brotherhood and sisterhood and anyhood, right? Anyone's welcome to the hood. Let's just go to the hood. You got to be part of the hood to understand what's happening. So, right? And so this is, rho is equal to AS over BD, right? What do you use when it's a T section, right? Because this looks like a ratio between the area of steel compared to the effective area of concrete, right? B being this distance, and then D being this distance, right? The distance down. Like in a rectangle, that makes sense. If I have the rectangular member, and I remember it now, right? And then D is the distance down to where the steel is at, and this is B, and then, that's D right there. And so that's B and D. And so the area, so you could say, well, what is the, I like how I'm doing this where it keeps disappearing. Right? This area right here relative to the area of how much steel I put in there, right? That's usually what this is. And the P on this, the P refers to the pre-stressing. So the area of the pre-stressing, I guess that'd be ASP over BD. And so then what do you use for BD? Because I'm going to give you one where it goes down into the web, right? So it's not going to be just the same width as you go down. So then what do you use for that B? And you're like, oh shit, doesn't tell you. Doesn't say anything about that in the code. And so then everybody gives the different values, because then it'll give you different FPS values if you use a different rho P value. But I'm going to tell you right now, it's still going to be this. Because if you look back, three of you will do this. Look back at structures 2, right? Look back at structures 2, and you'll see when we first developed this equation, it looks like this is an area, but it's not. The B comes from the effective width of your block, right? And then the D comes from the distance down to the steel. They're coming from different areas for different reasons, right? Even though it looks like it's an area, it's not. I would make the argument that in your homework, you would use this same width. Even though it dips down into the flange a little bit, it barely dips down to the flange. And so the most effective part is going to be the overall B, the overall width that you use for your thing. So when you get to that point right there, use this. It's the area of the pre-stressing over BD. Don't do like some people in the past have said, okay, well, I'll do the average area between this one and this one. Well, that's not necessarily right. And then someone says, oh, well, you can find like the centroid of it, and those are real nerds. Don't do that. Just use the effective, just use the width over there, because that's the part that this is the width of most of your compression block compared to the depth down to the pre-stressing. Perfect, right? So just do that. Okay. But anyways, that just points out that the code, that's where it becomes engineering judgment. I think Tim talks to you about that a lot. There's a lot of times you'll get called upon to be like, oh, and sometimes the code does it on purpose. They're like, oh, we don't really know. Let them do it, right? Let them make their opinion on which is most effective. And that's my opinion on what you would do there. I'm a doctor, so definitely listen to me. Right? Okay. So there's that equation. So then, let's see some other stuff. If compression reinforcement is considered for the calculation, FPS equation 20.3.1. So if you have compression reinforcement in there as well, it changes it on what to use for some of these values. And we're not going to do it with compression reinforcement. Also, the other thing that's a little foreshadowing, what you use, the prime there talks about, it's the area, it's the row.
This commentary 20.3.
Yeah, I was just looking at that because it's the compression. Well, the one thing I got, I'll tell you, I think that this is, in this case, because there's this row and there's row P, and I think that this row ends up being the same as this row. But if you had normal reinforcement in there, then this row would have the normal reinforcement and the row P. But for our example, I think they end up being the same. Because you just basically, the amount of regular reinforcement we have is 0, and so it ends up being, those end up being the same, right? And then this row prime is how much compression reinforcement you have in, which we, in your example, will not have compression reinforcement, so that this value would just be 0. Okay. I'm sure that clear as mud. Oh yeah, and then there's this, and then an added thing, right? Putting a limit on it. This value would not be less than 0.17 if you have compression reinforcement. No matter what, it would limit out at 0.17. Again, just part of this empiricism. When they did all the testing, they found that there was some limit on that. All these nerds doing deep research in concrete. I have one equation. When we go into bridges, I have one equation from all of my PhD and all my over 30 years of doing structural engineering. I got one equation in AASHTO. And unfortunately, they don't call it the Berry equation. I really wish they did. It calculates buckling in longitudinal reinforcement on circular, spirally reinforced concrete columns. Modern ones, not old ones, just modern ones. And then they have it, and then there's the equation, and then there's a footnote, and you look up in the back, and there's my name. I did it. We'll see it, man. It's awesome. We don't use it. We're way too deep for this class, but I'm in there.
Trademark the equation.
And so I call it the
variable.
Yeah.
And then also every time they use it, they have to ask you if they can use it.
You know what they would do? Fucking pull it. They'd say, they would say, this doesn't matter anyway. Fuck it. Right? Okay. So then that's how you're going to do it. So your homework, you do it. One, we just assume it's FY, and one, you assume it's FPS. You calculate this. Again, as I just laid out, that's not easy to do because there's a bunch of variables you have to calc, right? I can see an Excel spreadsheet or MATLAB that does this, okay? This is the strain compatibility. This is my baby, okay? And Stanton spends a bunch of time talking about this, but it is, it pains me to say this, it is academic, right? It's purely academic. It's so fun, though. Purely academic, right? And we're just going to skim it. Okay. I'll at least set it up, and then we won't talk about how to solve it. Like I said, I haven't quite worked out how much I'm going to show you here, so we'll just make it up as we go along. So we assume that this is 0.003. That distance there is x. We don't know what that is. You know what this is down here. All right, we'll call that epsilon sub pu. Right, when at this thing right before it fails, it's going to be epsilon sub pu. Right? And then that's going to cause stresses that look like this. So this all stays the same. This is all the same things that are happening. FPS, and this is 0.85 F prime C, and this is the distance beta 1 times X. Oh, we're out of time. Okay. We'll take it off from there next time. But I think just with one graph, I'll kind of show you how you would actually do it, right? And then we'll call it, and we'll say that's not how we're not going to do it, but if you wanted to do it, you could do it this way. And we'll skip a couple pages ahead, and then we'll jump on to shear capacity, right? Which is the shear capacity is, she's deep. She's deep. It is probably